We've looked at numbers, and computers work with numbers exclusively, certainly internally. But obviously, as you can see on the screen, there is text. So how do we get from numbers to text? The computer stores numbers, and then at some point there's a translation whereby we say this number represents a particular letter. This number represents another letter. And that's it. That's how it works. Obviously, we need to look at some of the details. So one of the basic translations of numbers to letters is actually really quite old by computing standards. The American Standard Code for Information Interchange dates from, I believe, sometime in the 60s, where computers looked quite different, but it was actually used for transmitting information across networks electronically, where it would be printed out pretty much instantly. There was a small amount of storage before it would just be printed out onto paper. And this then got inherited in computing as a way of encoding letters and words on computers which use numbers. So all computers will be able to handle ASCII. All modern computers nowadays know what ASCII is. It's just in there, it's in the basics of it. They can use it. And ASCII has a representation for numbers, which sounds odd because we're starting with numbers and then we're making them numbers. More on that later. For letters, both lowercase and uppercase. And various symbols, punctuation characters, and also a whole lot of control characters, stuff that may seem a little odd. But if we think back to what I just said about how this was initially used, not on computers, but for transmitting to some sort of printer where it would almost instantly be printed out, then this starts to make a little more sense. One more thing to consider is that even though we commonly use 8 bits in a byte, this coding uses 7 active bits, and there's 1 bit left over for something called parity. So it actually only uses 7 of the bits in there to encode the characters and text. And this is what it looks like. Isn't it interesting? So let's just quickly go through these columns. So this is what the number actually is, the decimal representation of a particular number. And here we have the hexadecimal representation, which is a little unnecessary perhaps right now. And here we have the binary. We've spoken about binary earlier. So if we have a binary number that is equal to 0, so we have 8 zeros there, which in hex looks like 0 as well, and in decimal it's 0, and it means null, which is handy. That's good. And then the number 1 means start of header. It doesn't mean 1. It's one of these control characters. And then start of text here is 2. So to begin with, we have a whole lot of stuff that just isn't text. It's related to the transmission of text. We even have bell. This will actually make a bell noise or instruct the machine to activate its bell. Backspace and tabbing. We even have delete down here at 127. So there are a whole lot of these numbers that actually don't represent the text per se, but rather some sort of control of the machine. And then as we start moving further along the list, so the number 32, space. Now that feels more like text. Now we're getting somewhere. This is part of a word, and we have exclamation marks and so on, some punctuation stuff in there. And then by the time we get down to the number 48, or 30 in hex, that's the number 0. Written as a character that looks like a number, but is actually some text. So 48 is 0, 49 is 1. Now, obviously, this is, in many respects, madness, and a lot of people don't like this, but it's something we're stuck with. The computer has to deal with it. There are good arguments to say that they should be different, that we should actually have the numbers to begin with, and then you could just smoothly and fluidly transition over into text, backwards and forwards between binary numbers and text without having to go through this strange translation. But that's not how we have it. Instead, we have this. And ASCII lives on today. We just go down the list here of standard characters, and here we get down to our capital letters, and then the lowercase letters are here, and we're done. And the observant amongst you will see that we only go as far as Z. There are no other letters, and this is one of the limitations of ASCII. We've spent a lot of time with some strange characters that don't seem to do anything of any interest for us anymore, and we don't have any of these extra letters that even within European and Latin alphabets exist. We don't have those, which is obviously a limitation. This is also one of the sources to the problem we have when creating file names and folder names in certain programs, ArcGIS, especially ArcMap as well, older programs or code, old code that still exists in modern programs, where the addressing, or rather not the names for the in the path to find a file are actually based on this ASCII table. So we can't have strange letters in there. This is obviously kind of a limitation in the modern world, and so there are extensions to this. So modern extended ASCII has a lot more characters in there. So we have, in my example here, the Swedish letters or and then symbol for quarter and a half, stuff like that. But actually, not just the extended ASCII, which is otherwise known as ANSI, but UTF-8 Unicode, which you may recognize as well, or recognize the name at least, is essentially an extension of ASCII, and it is now the most common encoding used in terms of websites and programs and computers. So, but it is in many respects identical to begin with, the first 127 characters, and then there's a lot more happening afterwards, so that we can get these other characters in there. So that's fine. Let's just quickly look at what's happening when we encode text. So how do we write the capital letter H in ASCII? It looks like this. So that's a string of bits stored on the computer, and that's an H. Good. And then if we want to write the word hello, we need an H, and then we need a lowercase e in this case, and then an L, and an L, and an O, and it's a very long string. All of that is required to store the word hello. So it's on the computer, stored like this in one long string, but then we need to translate it. We need to go to this table. So we need an instruction. And as we said, if this is ASCII, then it takes 8 bits at a time. It takes 1 byte. And it says that word is a letter. So we take these 8 bits, this byte, and that's it. And we'll translate that into a letter. Others, like UTF-8, might want to take 2 bits or 3 bits or bytes, sorry, 2 bytes or 3 bytes or 4 bytes, and say, this is 1 letter. We need all of those, and we're going to translate all of those into a letter. But let's just stick with the simple case here, where we have our ASCII encoding of hello. So the computer takes in this stream of bits and says, after 8 bits, stop. Okay, that's 1 letter. Next 8 bits, stop. Yep, thank you, that's 1 letter, and so on and so forth. Because we've instructed it that this is ASCII, and it's 8 bits at a time to make a letter.